speed and velocity. As we said before, speed is the scalar, velocity is the vector, so there's a direction. And there's this idea introduced here of average speed. So for average speed, you just need the total distance and the total time. It's the same with average velocity. Average velocity is the displacement. Now that's with reference to where you started. So if you've done a full circle, even though, say, you've gone 400 meters around the outside of the football field, if you end up back where you started, your displacement is 0. So your average velocity is 0. Right? Your distance was 400 meters, but your displacement was 0, and therefore your average velocity is 0. So that's something to watch out for. Displacement here is referring to from your starting point. So where are you now at the end compared to where you started? Right, during that time, you might have gone faster, you might have gone slower, you could have changed direction. A change in direction is also a change in velocity, not just a change in the speed component or the magnitude component. So if you change direction, you're also changing your velocity. Right, so here we've got, if the rate of change is measured at an instant in time, then this is the instantaneous velocity. And I think I've connected to your lesson plans a little video that talks about a guy running home and how his velocity changes. It'd be good to have a look at. Right, so in this question here, person rides a bicycle 6.5 kilometers east and then 2.5 kilometers west, and the trip takes 2.5 hours. So if you were asked for the distance, it's going to be 6.5 plus 2.5. It's going to be 9 kilometers. But if you're asked for the displacement, then it's only going to be 4. So it says total distance traveled, 9 kilometers. Average speed, well, he went 9 kilometers in an hour and a half, so 6 kilometers an hour. That's what they've got here. There's no direction in those. Distance and speed, no direction because they're scalars. Displacement is 4 kilometers east, or you could go plus 4 kilometers. Either that plus or the east has to be included to show the direction. Right? If you're going to use the plus, I would expect you to say up here that I'd just put east positive so that I've shown that east is going to be positive. Or you can put an east here in your answer. Either way, average velocity, you want your final displacement, which is 4 kilometers, and the time 1.5 hours, so 2.67 kilometers per hour east. Right? Now, in this sort of question, you're probably going to stick with kilometers an hour. Later on, we're going to be doing some more complicated equations, the equations of motion. I think I've already done the video on that. You need to have those in meters and seconds. So as a general rule, I think it's a good idea to change to meters and seconds. Righto, we looked at these sorts of graphs last year. Hopefully everybody did that. This first one is a graph of constant velocity. So we've got displacement and we've got time. So the change in displacement, because velocity is displacement divided by time, the slope here gives us the velocity. Right, so if I just show you the slope on that graph, displacement is on the y-axis because slope is change in y over change in x, rise over run. So y is displacement and x was time. So that would have been meters divided by seconds. It's meters per second, and that is velocity. Right? If it's a nice straight line like this, that means that our velocity was constant. So that's the graph for constant velocity. Right, over here, you have got a situation where they've run out a certain distance, waited a certain distance, or not distance, certain time, and then returned back to the start. Right, that negative slope there shows you that the velocity will be negative, and the negative really is just indicating the direction. All right, there's a little trick if you have a velocity time graph. So if we look at a velocity time graph, velocity time, the slope is going to be the change in y over the change in x, which is going to be the velocity divided by the time. So that's meters per second divided by seconds again, meters per second squared, which is acceleration. Right, but if you look at this, the area under the curve for a particular time, that area is going to be area of a triangle is a half base by height. So that would be a half time by velocity. So that would be seconds times meters per second. So the answer is actually in meters. So it's displacement. So if you're looking at this graph here, a velocity time graph, you can get the displacement from the area underneath. Righto, these little graphs down the bottom are important. For an object travelling at a constant speed, the graph shapes and their properties. So this is displacement. S is for displacement because D's already used for something else. Displacement time, so that would slope of that gives you constant velocity. This one is showing a constant velocity because it's a velocity time graph. So the slope for that will be whatever this value here is. Constant velocity of 6, and the slope of that is going to be velocity divided by time, which is acceleration. So say that was 6. So constant velocity, you read it off here at 6. The slope, it's constant speed, so there's no acceleration, constant velocity, no acceleration, slope is 0. And the area is going to give you the displacement. This one here, these three are all of the same situation, an object moving at constant velocity. If it's moving at constant velocity, there's no acceleration, so it's just along the 0 line there. These graphs over here, non-constant speed and velocity, this is actually a regular shape, right? So this is something undergoing constant acceleration, uniform acceleration. If we want the velocity off that, we're going to have to work from the tangent. So you just draw on a tangent and read it off, but that's not the situation we usually use.